Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad and Shazim bin Ahmad Walizan. I'm an analyst at 8088. And for the introduction part, we mainly focuses on converging nozzle and compressible flow. So compressible flow only occur when fluid density changes significantly and the convergent nozzle accelerated air by reducing flow area. So in this presentation, we also focuses on CFD parts, which is the computational fluid dynamics to predict our pressure, velocity, and density and Mach number. So next is objectives. We have four objectives, which is first of all to understand compressible flow behavior inside a convergent nozzle, and to perform CFD simulation using NC's fluent, and third, to study the effect of nozzle pressure ratio on flow characteristic, and finally, to compare our simulation with published research for validation. Okay, so for the theoretical background, first we start with compressible flow, where the density of air changes due to pressure and temperature variation. So compressibility becomes significantly when the Mach number exceeds approximately 0.3. As the air accelerates through a convergent nozzle, the pressure decreases while the velocity increases. So when the flow reaches Mach 1, it becomes choked, meaning the maximum mass flow rate has been reached. And the second concept is Mach number, which is defined as the ratio of the flow velocity to the speed of sound. It is important parameter used to determine whether the flow is subsonic, sonic, or supersonic. So another important parameter is the nozzle pressure ratio, or the NPR, which is the ratio of the inlet total pressure to the ambient pressure. So increasing the NPR causes the flow to accelerate, and once a critical value is reached, the flow becomes choked. And finally, the CFD part. So the CFD is used to solve the continuity, momentum, and energy equation numerically. So in this project, CFD predicts the pressure, velocity, density, and Mach number distributions inside the converging nozzle, allowing us to analyze the flow without performing physical experiment. Okay, so next is literature review. So the research paper that our group selected is entitled CFD Analysis of Compressible Flow Through Convergent Conical Nozzles by Spots, Guzik and Gao. And the researchers investigated compressible airflow through convergent conical nozzle with cone half angle of 15 degrees. They performed CFD simulation using ANSYS Fluent while varying the nozzle pressure ratio of NPR, which is 1.6, 1.8, 2, 3, 4, 5, 6, and 7. So the study evaluated the important performance parameters such as mass flow rate, discharge coefficient, thrust coefficient, and flow behavior inside the nozzle. So the results show that smaller nozzle cone angles produce high discharge coefficients, while increasing the nozzle pressure ratio accelerated the flow until choke flow occurred. So the CFD predictions also show good agreement with the experiment data, demonstrating that CFD is a reliable method for analyzing compressible nozzle flow. So our project is based on this research, and we replicated the 15 degrees convergent conical nozzle and performed simulation up to NPR that I stated just now, and compare our result with the published findings to validate our CFD model.
The model replicates the primary nozzle configurations from the benchmark study. It is designed as a two-dimensional asymmetric convergent conical nozzle for high-speed compressible air. The geometry includes an upstream fluid approach section followed by a linearly converging truncated cone. This specific shape is designed to accelerate subsonic flow toward the exit plane or throat. The computational domain is modeled along a centerline axis to optimize computational efficiency while leveraging flow symmetry. The design uses a detailed approach profile rather than a sudden area change to mimic realistic experimental setups. The approach section inlet diameter is 145.48 millimeters, while the nozzle exit plane throat diameter is set at 76.2 millimeters. The nozzle cone half angle was set to 25 degrees relative to the center axis of the symmetry. The total exit area was kept uniform to isolate the aerodynamic effects of varying pressure ratios. The upstream boundary extends 574 millimeters upstream from the exit plane to establish a fully developed boundary profile. The downstream boundary extends 7,626.6 millimeters downstream from the exit to allow for supersonic shock diamond formations to resolve without interference. And the radial far-field boundary was set at 1,803.4 millimeters from the axis of symmetry to clear any lateral jet plumes or dissipation boundaries. The computational domain was discretized using phase meshing with an element size of 0.025 and a quadrilateral dominant configuration. The nozzle entrance was designated as the inlet, while the exit orifice was defined as the interior. The top of the external boundaries of the nozzle, which consists of the horizontal and one diagonal line, were defined as walls. The entire bottom line, spanning both the nozzle and the extended ambient domain, was set as symmetry axis. The left, right, and top edges of the extended ambient fluid domain were collectively assigned as the outlet. The simulation utilized the ANSYS Fluent pressure-based solver, configured for a planar steady-state analysis. To capture compressible flow physics, the energy equation was activated and the realizable K epsilon viscous model was selected. Inlet conditions are such that configured as a pressure inlet to test variable nozzle pressure ratios, NPR, with the temperature set to 288 Kelvin, turbulent intensity at 0.1%, and a turbulent viscosity ratio of 1. Outlet conditions were configured as a pressure outlet using default pressure values alongside a backflow temperature of 288 Kelvin. The solver underwent standard initialization starting from the inlet conditions and was executed for 1000 iterations to achieve a steady convergence.
From the following comparison, several similarities can be observed between the CFD simulation results of compressible flow to a converging nozzle. The reference paper uses Metacom CFD++, while this study uses ANSYS Fluent, which is the software more familiar and accessible to the students. Both cases using the same geometry conditions, which is a converging nozzle at a 25-degree nozzle angle and a nozzle pressure ratio of 7.0, which allow for direct comparison of flow behavior. Although there is slight differences in numerical value, the overall Mach number distribution shows an inconsistent trend in both simulations. At the inlet, the reference study shows a very low Mach number, while the ANSYS simulation gives a small but different initial value. This difference is likely due to the variations in boundary conditions and numerical setup. However, both results still show the same compressible flow behavior, where the fluid accelerates through the narrowing nozzle and reaches near Mach 1 at the throat. Downstream, Mach number continues to increase in both cases due to conversion of pressure energy into kinetic energy. The reference paper predicts a maximum Mach number of about 3.0, while the ANSYS simulation by the students gives a slightly lower value at 2.48. Despite this difference, both results still captures the same acceleration trend. Near the outlet, both outlets shows further expansion and increasing Mach number. The reference study reports a higher value compared to the ANSYS result, with a larger deviation in this region. This may be due to differences in mesh refinement, turbulence modeling, and boundary conditions. Overall, the comparison shows good qualitative agreement, indicating that the CFD model developed in this study is able to reasonably replicate the compressible flow behavior reported in the literature review. Thank you. The two figures show the distribution of Mach number for a converging nozzle at angle 40 and NPR4. From the reference paper, the Mach number contours are smooth and clearly illustrated in the acceleration of compressible flow through the nozzle. The flow enters at a low Mach number of about 0.4, accelerates through the throat, and continues to increase downstream. The contour distribution is also very uniform, indicating a stable and well-resolved numerical solution. The highest Mach number is in reference case reaches approximately 11.6 near the outlet region of the throat. For the ANSYS Fluent simulation performed in this study, the overall flow behavior is similar. The flow accelerates as it approaches the throat, reaching the peak Mach number of about 1.8 before expanding downstream. This confirms that the CFD model is able to capture the expected compressible flow behavior in a converging nozzle, with the highest velocity occurring after the throat region. However, there are quantitative differences between the two results. The reference paper reports a maximum Mach number of around 1.6, meanwhile the present simulation predicts a slightly higher value of 1.8, corresponding to an error about 12.5%. Although this deviation is relatively small, it indicates a slight over-prediction of flow acceleration in the model done by the student. These differences can be attributed to several factors, including the use of different software, variation in meshing, quality due to limited experience with advanced meshing techniques, as well as the restriction due to computational resources that prevented finer mesh refinement. In addition, minor simulation errors and differences in available tutorials for the newer version of ANSYS Fluent also contributed to the challenges in reproducing the exact setup from the reference study. Overall, despite these limitations, the CFD result still shows good qualitative agreement with the reference paper and successfully captured the main flows of fluid kinematics. Thank you. From the following figures, the effect of varying nozzle pressure ratio (NPR) can be observed through the maximum Mach number and the development of the jet plume along the bottom axis. First of all, at low NPR value of 1.6 and 1.8, both cases remain fully subsonic with a peak Mach number of 0.181. The flow is smooth with no shock formation and the jet plume appears relatively stable with NPR 1.6 showing a slightly more elongated structure compared to NPR 1.8. The jet plume refers to the stream of fluid exiting the nozzle into the surrounding medium, and its shape depends on the flow velocity and the pressure condition. At NPR2, the Mach number increases to about 1.05, indicating the onset of supersonic flow. A small supersonic core begins to form at the nozzle exit before dissipating downstream. From NPR3 onwards, the flow becomes more increasingly supersonic, with clear jet structures and the formation of expansion and compression region along the jet core. As the NPR increases further to 4.0, 5.0 and 6.0, the maximum Mach number rises from 1.85 to 2.48 and distinct shock cell structure begin to appear and become more defined. At NPR 7, the flow reaches a maximum Mach number of 2.82 with a well-developed and extended shock cells downstream. Overall, increasing NPR lead to a clear transition from subsonic to supersonic flow. At higher pressure ratio, the strong pressure difference between the nozzle and the atmospheric pressure causes the flow to expand rapidly, forming characteristic shock diamond patterns due to alternating compression and expansion regions. Thank you. To conclude, this assignment successfully relates the concept of fluid kinematics to compressible flow behavior in a converging nozzle. From the simulation, it is observed that when the pressure ratio is sufficiently high, the flow reaches Mach 1 at the throat and becomes more supersonic only after exiting the nozzle, where it expands into open atmosphere and develops more complex flow patterns. Using computational fluid dynamics, the flow behavior was analyzed and compared with published literature. The nozzle geometry and meshing were developed based on the reference study, allowing for a consistent comparison. The result also demonstrates how both nozzle geometry and nozzle pressure ratio significantly influence the flow and flow characteristics. A converging nozzle accelerates the flow through a narrowing passage but imposes a physical limit when the flow can only reach Mach 1 at the throat. Beyond this limit, further acceleration depends on the pressure ratio. At higher NPR value, strong pressure differences lead to more complex flow structure and alternating expansion and compression patterns downstream. Overall, CFD model developed in this study successfully captures the expected flow behavior and provided a good understanding of geometry constraint in compressible flow. Although there are slight differences compared to the reference paper, this study offers valuable insight into nozzle aerodynamics as well as the practical challenge of CFD simulations, including meshing difficulties, computational limitations, and long simulation times. That's all. Thank you.